Okay, let's start. So today we are continuing to talk about LC3. So curiously, we um, stopped at a branch instruction. So for the branch instruction, the CPU first read the C, is a part of the ALU, and then evaluate whether we needed to take this branch or not by the three registers, the content in the three registers. These three registers send a select signal to this PC mask. And the mask has two inputs. Okay, these three registers is the signal. And besides this, the input of this mask is +1. The PC +1. All, which means that we will sequentially run the code. Or we take this branch, we add a offset. This is the offset to the PC, so that you can do the jump operation. So here is one example. This example is used to compute the sum of 12 integers. The number starts at the location of this address, and the program starts as the location of this address. You start from moving initialize, and then you use the register 2 as the evaluator. If register 2 is equal to 0, which means that you finish the 12 number addition. The accumulation of 12 number. Why? Because first you initialize the R2 12. So it's a kind of a counter. When you finish one accumulation, you do this until it reaches 0. If it's reached 0, then you can stop. Finish the accumulation. Otherwise, you continue to do the accumulation. And R1 is actually the index of the numbers. Because the number start from this graph. At the beginning, you initialize it to this graph. So R1 is this 12 integer, first integer among this 12 integer. After you complete one combination, you plus a 1 on the R1. And you also use R1 as an index to read the next number you will add on the results. And the R3 is used to store the temporal accumulated results. At the beginning, it's 0, and then you just add a number to R3 again and again. R4 is the number, the current number you want to add to the accumulated results. So this is R. And this is a simple loop. And this is the condition whether you need to continue to do the loop or not. Again, the whole program, this is the data flow of this program. The whole program can be conveyed into these memories. So each instruction indicates one operation in the previous figures. So you can see that the program actually. Here we have this. Then you can run it for one. And all the instruction again will be compiled into binary. This is your opcode, and then you have different records based on the type of your instruction, based on the opcode of your instruction. Again, you can check the manual of the LC3, and then you can understand what's the meaning of. The last instruction is the unconditional branch, which is the jump. So you always take the branch. And the target address is the content of a register. Allows any target address. So this is the opcode of the jump. And this is the register used to solve the operation here is very simple. You just read from this register. Right. So the next instruction will run. And then we also have a cap. Cap is used by the operating system. But you have some services provided by the operating system. You can use this instruction. This is the opcode of your type instruction, and this is the type of the service. For example, 23 indicates input a character from the. Here is a new character. 21 means output. 25 means you hunt on a program. So because this is a very simple instruction type, we only support these three services. So these are the interface between the OS and the instruction. when the OS function or the OS routine is done, the PC is set to the instruction following the trap. You complete a OS routine in that case. We will talk about the OS more in the future lecture. So here is one example. One program can count the number of a character in a file. So the program begins at the location of this address. And then it starts to read character from keyboard. And load each character from a file. The file output is a sequence of a memory location. Because it's consecutively stored in the main memory. The starting address of the file is stored in the memory location immediately after the program. So the program starts from this address. It will end. The program will end this address. And then the file will start from after that. So if file character equals to the input character, you just increase the counter. At the end of the file, there is a special asset value, which is a character. At the end of the program, you need to print the number of character and stop. And in this program, you see that any character, the number of any character will be smaller than 10. So this is the control flow of this program. And the difference between this program and the previous program, major difference is that you need to do this. But for the loop, it's similar. You also need the condition is maintained by one fracture. I'm sorry, by one register. If register satisfies some condition, then you can continue this loop. Otherwise, you just turn out of this loop. And then this program also can be compiled into binaries like this. This is a long program. From this program, you can see this is actually the data layout of this program in the main memory. The program starts. And then it ends at this address. So totally there are 18 instructions. This is the hash number. And then this is the starting address of file. So you can copy this program and try to run this program on the LC3 simulator. Yes.
So the instructions for size is 16 bit.
Yes.
So each instruction should take 2 bytes.
Yes.
So the second address should it be 3003?
This is the address of one instruction, and each instruction takes 2 bytes. This is the minimum unit is bytes. This is the you cannot address one of the bytes. Each time you can address. Each time you can address. That's minimum unit.
So, address,
Like what you said, this is a tool, right?
yes,
Then how about the you issue a 3001? If you want to read it.
so the byte number 3000 and 3001 should occupy the whole section because it's 16 bits. So,
This is the main memory layout. In the main memory, you need so the graph is used to index minimum.
so this is not the byte number.
No. Why is not the byte number? Because you cannot read each byte.
Right.
Each time you only can read a minimum of 2 bytes. If you just want to read the second. That's right, that's right. So you can actually copy the code and try that code on C3 simulator, which is called penny sim. You can download the penny sim from our canvas. And I also attach a manual and description of the simulator on canvas too. I will post an announcement after this class to help you to understand how to use that simulator. So basically the simulator is just one of the implementations of LC3 instruction set. And this is the hardware component of the LC3 instruction set. The entire instruction set can be implemented like this. And our simulator is just one of the implementation of this. It can simulate this. And you can also Google LC3 simulator online, and you can find some other type of simulators. But all the simulators need. The major part of this is the ALU. It can support addition, and not. We have a PC and the PC max. We have 8 registers here. Register, yeah. But 8 registers contained in one register file. We also have a control unit here. Besides this, we have a main memory. The memory can be accessed by 2 registers. One is the memory data register, the other is the memory address. We also have input and output, including a monitor and keyboard.
If we want to output something, where should we put the vector in which register we put the vector?
You need to, you can put your data in any register, but after that, you need to invoke the trap.
So how do you know that which one to output?
Okay, this program can help you understand that. For example, you can put your data in R0 and then run this trap. I believe you can output your data on monitor.
If I put it in R1, then
you can also do that, I believe so.
So how will you know that which one to generate?
You can specify that in the application. I believe your question can be answered by the description of the simulation. And all the components of LC3 are actually connected by a global bus. The global bus has a width of 16 bits. So you can see that actually almost every component can be connected to this global bus. Register file, memory, I/O, PC, ALU, all major components can be connected to the global bus. So the bus has a control. Only if you enable the bus can help you transfer one signal. And each time the minimum unit of data bus support is 16 bit. If you just want to transfer one bit, you have to use 16 bit. And if you have a more than 16 bit, you need to transfer data in multiple cycles. Again, any number of read the bus simultaneously. We also have a signal to control whether we can write or not. That's the write enable signal. But this write enable signal is actually controlled by the unit. The memory part actually contains the control and the data register for the memory and I/O devices. The memory can be accessed by two registers. ALU can read some data from the register file. Again, it's assigned to something form. And the output will also go to the bus, so that the register file and output will receive that output of the ALU. For the register file, it can support two read operations simultaneously, and one write operation each cycle. For example, if your instruction needs two output operands, which means that you need to access the top register 1 and top register 2. You can read these two numbers in the same cycle. The register can also receive some input from the class. For example, ALU can generate right back. Again, the ALU PC memory address all numbers from the register files. And the most important part is the PC. Because the PC points to the instruction, CPU will run in the next cycle. There are three inputs for the PC. One is a selection because it's controlled by the PC memory. The other two is sequentially run offset. You need to jump to one offset. And the memory address register also has it also has three it also has two inputs. One is the load and store. The other is you can look up this type of load and store in the previous several slides. The difference between these two load and store is the addressing mode. One is a PC relative, the other is base and offset addressing mode. So the memory address register also has to support this instruction register for the track instruction. We will show the detail in the following slides. In order to support the branch instruction, we have three registers: negative, 0, and positive. This three register is actually generated the control signal for the PC mask. A register set only when the control unit is enabled. So only the control unit contains the content in three. And only these instructions have the control unit is one finite state machine in the instruction set. Each cycle it will change the control signal for the next phase of instruction processing. So the control unit need to worry about all the details actually of the components in the instruction set. It also needs to in order to do that. So when it receive one instruction, it will decode the instruction by looking up the content of the probability. And then it will know that how many registers I need to write in this cycle. Whether there is an immediate number in this instruction. Any question about LT3? I believe most of your questions should be able to be found in the description of this instruction set. And I have already posted it on the canvas, but I will send you another announcement to remind you.
What are you referring to or one?
Not homework. A page,
Oh, that's a little here.
yes. So after you have the instruction set, the next step is to program on the instruction set. The programming actually means assembly language programming. Where you have no compiler and all high level language. Which means that you can do the programming in the pure slice. In order to solve some problem, we need to do on a computer. We need to convert an algorithm into the LC3 machine instructions. And of course, we need to do the debugging. But the LC3 simulator does not support a very fancy debugging function, which means that you cannot set a breakpoint on the simulator. But you can still do some lightweight debugging by intermediate results. And it also can show you the content in the register every cycle. So you can run the simulator cycle by cycle so that you can know what will happen in each cycle. So when we have a very large problem, we need to understand the problem first. Here is one example. We need to count the number of occurrences of a character in a file. And then the character in the question is to be input from the keyboard, and the results will be displayed on the monitor. When we have this large problem, we need to decompose it into multiple simpler subtasks. And we can continue to decompose each subtask into a smaller subtasks until you have all the tasks written even by the memory instruction. In order to solve a problem, you need to find, which means that you need to draw a control flow, like what we did in the previous slides. So here is one example. When we have a task, we have three different styles. First one is I break it into multiple steps, and each step, all the steps here are sequentially connected. This means that you can do all the steps here in one line. Or you can use some condition here so that you have some branch based on the value of the registry. You can do this, or you do this. Or you can use the loop to solve the problem. You use a register to control whether this loop can be continued, or you can keep this loop to run the code after this code. For the pressure display, you can break the class into different steps like this. This is the simplest programming mode. So for the second programming mode, you can use the condition here. You evaluate whether this condition is true or not. You run different codes. But only one of them will. Eventually, the body of the application will be run by a loop. In this loop, you always check the next to see whether it's a match or not. And when you have another these three programming modes to decouple your problem. After that, you can use the instruction level language. So each subtype. And I will provide you more example by posting some example programs. By example, you can actually run those example programs. In that way, you can get familiar with the simulator itself. And the program here. I will post the 3 types of programming, including the sequential, conditional, and integration. Any questions? These should be very easy for the computer science major students. But if you are from a biology background, you need to check these slides. Any question? If no question, we can stop today. Thank you very much.